doing here, but by 10 o'clock, we'll probably have to go a little bit for tomorrow too. I don't think we'll get through both of them, through everything, but let's see what we can do. All right, so I gave you a second worksheet on your, so here's worksheet number, there's worksheet number 2. That one is actually, it's basically going to be the same thing we're going to do, but I think it works a lot easier if, did I give you the answers? I think I gave you the answers on worksheet number 2. Did I give you the answers for worksheet number 1 too?
No.
Okay. That worksheet number 2 does have the answers, so if you want to practice it up, you can. But we're going to look at them as being the actual circuits. But that's what those numbers are actual circuits. But it makes a lot more sense if we use our schematics. So basically, when we're first looking at an RC circuit, this is what we call an RC circuit. And we have a resistor and a capacitor in series. And then we have our voltage source. Now, our R value, that's going to be our plus X value. It's always going to be plus X. It's always going to be right here. And I already labeled all the vectors already. Everything that we're going to be working with, I already labeled what the values are going to be for our plus X. So R is always going to be our plus X. Our capacitor is always going to be our negative Y. That's always going to be negative Y. That's going to be down here. That's where our capacitive reactance is going to be down here. And then so R and C, those are going to be our rectangular functions. And they always are rectangular functions. The polar function then is going to be our resultant. That's going to be what my voltage total is. What my current total is, my voltage, my impedance total, my power total, and then what my angle is. So let's just get through one here and we'll kind of go through the theory of it so we can see what's going on. All right, so in my calculator then what I want to do is I want to start finding out some of I want to fill in the rest of my blanks. Okay. Right now I know that what's given is I got my resistor value and I have my capacitor value, or my capacitive reactance. Not my capacitor value, that's not fair, that's my capacitive reactance. That's based off of whatever my frequency is. So don't get that confused now. We're jumping into capacitive reactance, not my capacitance. So that's going to be my Y value. So if I know my X and I know my Y, then I can find my Z, I can find my resultant. We can find our impedance total. So using your rectangular to polar function, what you're going to do is you're going to go and hit in 3 kiloohms, hit your second XY, put in 4 kiloohms, that's going to be your negative Y, and then you're going to hit your second and go to rectangular to polar function. And what's going to happen is that we know that we're going to be in quadrant number 4, and we're going to get some angle and some length on that line. So for example here, my R is going to be at 3, so I'll just go 1, 2, 3, we'll just do it, that one's make it a little bit more. We'll go, so we're going to say, here's my 3 kiloohms. And I got 1, 2, 3, 4, 5, 6, 7, 8. And then I got my 4 kiloohms. Okay, so that's going to be where my vector is. I know where, so here's my 3 kiloohms for my resistor, so I went 6 times over, so that each one of these is worth 500 ohms. 500 ohms down this way, and I'm just going to place a dot right where those two would intersect. So I know that my length of my impedance is going to be down to here. And then I know that my angle is going to be somewhere from here to here, and I know that this is going to be, let's put this in, 0 degrees, this is plus 90 degrees, and this is going to be negative 90 degrees. So I know that my resultant is going to be somewhere here, and I'm going to have some kind of an angle from 0 to a negative number. Okay, so I can either call this either 90 degrees or it's the same as saying 270 degrees. But our calculators are automatically going to just reference it from 0 and go swing it down and give us a negative angle. All right, so by entering this into my calculator, I get next, my resistor is 3 kiloohms, my capacitive reactance is 4 kiloohms. What do I get for the length of my line here? That's this one right here. That's going to be my ZT. That's going to be my impedance, which is a combination of. So So what do I get for ZT? So I go 3 second XY, 4 second rectangular to polar.
Yeah, 5.
5. Okay? Then it's 5 what? What's your units?
Okay.
5 kiloohms. Yeah. So my ZT is going to be my 5 kiloohms. Okay, when I'm talking about Z, now it used to be when we just had all resistors and stuff, we had considered our total resistance. But we don't have just purely resistance, we have capacitive reactance and resistance, and so we call it impedance now, because it's a combination of capacitive reactance and resistance. We call it impedance. That's in your book there, you can read that. Okay, so that's why we call it ZT. So ZT is basically our total resistance of our circuit. That's what this is what that power supply is going to see this circuit as in a certain frequency. The loading of that power supply would be of 5 kiloohms. All right. So now, our other thing that we want to know is what is our angle. So then on my calculator, I'm going to hit my second. I'm going to do my second XY again. And what do you get for an angle? Now watch, and remember that angles have polarity.
Positive 5.3.
Negative 53.13. If you didn't get a negative, it was because you didn't put your capacitive reactance as a negative Y. Okay? But your calculator should have gave you a negative 53.13. So make sure you put in your, when you're talking about your capacitive reactance, when you're doing it as a vector, make sure that you're putting it in as a negative value. Okay? So did everyone get that answer? Everyone good? Moving right along? All right. So now, so that we don't think that we always have to do a trig, we can also do everything as long as I'm staying within my component, whether it's my power source or my capacitor or my resistor. As long as I'm staying within that one component, Ohm's law still applies. So V is still equal to IR. So here we know our voltage and we know our resistance. Okay, when we're talking about our impedance, we're talking about our resistance. If I know my voltage and I know my resistance, then I can go ahead and I can calculate out what my total current is. So figure out what your total current is by just basically using Ohm's law. So now it should be I is equal to V over R. So what do you get for current? 3 milliamps? Okay, and then what's my units though? 3 milliamps? AC. Don't forget your units.
What is that? What's in our voltage?
Huh?
What's in our for the voltage?
15 volts. You don't have the worksheets either?
Do you know how to run anything? I told you I'll have to inside the box.
Huh?
I told you I'll have to inside.
Oh, there's still a couple of those extra worksheets. Those worksheets. I think there's another set of worksheets over there. Let's grab some of those. All right. So that's our basic Ohm's law. We can still use Ohm's law then at that particular component. Then, just like we did back in DC, what remains constant in a series circuit?
Current.
Current. So what's my current going through my resistor then?
3 milliamps.
So that still remains the same. We still, nothing happens there. So I still have, my current is still going to remain constant in a series circuit. So I'm going to put in 3 milliamps there, and my 3 milliamps AC here. Okay? So now I can do it either two ways. Now once I know two things, I can find my third using Ohm's law, but we already know how to use Ohm's law, so we're going to do it a little bit differently. Otherwise I could take my resistance times my current and get my voltage. And that's a good way of double checking it. But what we're going to do is we're going to do our this time what we're going to do is, since I have my polar functions, I have my total voltage, and I know my angle, I can figure out what my voltage is across my resistor and what my voltage is across my capacitor. So since we're practicing doing this in our calculators, what I want to do now is I'm going to put in my 15 volts AC, and then I'm going to hit my second XY, then I'm going to put in my negative 53.13 degrees, then I'm going to sit, and then I'm going to do my polar to rectangular function this time. And the first number I come up with is going to be my X value. And that's going to be my voltage of R. So VR is going to be equal to 9 volts, and what's your units? Volts. AC, yep. Don't forget that. Okay? Then if I hit on my calculator, if I hit my second XY again, then I'm going to get my value of my capacitor.
Or just 12 actually.
Yep, and now we ignore the polarity when we put it down because it's AC voltage. But when we're doing it in vectorly, then we have to put it in our calculators with a negative sign, but when we write down the value of it, it's no longer negative. This is 12 volts AC. Okay? Is everyone keeping up so far? Follow along? Alright. So now we only have, the only thing we got left now is our power. Again, our power formula always applies as long as we stay within our component. So let's just figure out our power across our source here. So what do I get for power just using Ohm's law? $45 milliwatts AC.
Yep.
Okay, and we're going to come back and we're going to talk a little bit more about, power as we go through. So, my total power so does anyone know if anyone read the chapter before today, does anyone know what our actual units is for power?
VAR.
VAR. So it's actually millibars. What it stands for is volts, amps, reactance. Okay? Because we're no longer purely resistive, I have a combination of a capacitive reactance and a resistive, and the combination gives me 45 millibars. So that's what you really want for an answer, is 45 millibars. It's the volts, amps, reactance. Then when we start describing how the circuit is working, we'll explain that a little bit more. But it's a combination of my capacitive reactance and my power of my resistor. Alright, so now, once we get our total power, then we can go ahead and use our polar to rectangular function again, and we can figure out our power across our resistor and our power of our capacitor. So this time you're going to use the 45 millibars, and then use an angle, again, of our negative 53.13 degrees. And then what do you get for power of your resistor and the power of your capacitor? If it feels a little chaotic, don't worry, we're going to do a couple more, but there's just so much a little bit more complicated than the old series circuit that we did in DC. But we'll practice these things. So what do I get for the power across my resistor?
So what are the two numbers that we're using again?
45 millibars in our angle. And we're going to go from polar to rectangular.
27 millibars.
Okay, 27. This is for your resistor.
Yeah.
Okay, this time it's going to be milliwatts. It's going to be our true tip. It is going to be milliwatts this time. Yep, and we're going to explain that. So it's going to be 27 milliwatts. That's our true power. and this time it's 36, and it's going to be milli VA, or both amps. Okay, 'cause both amps, remember it as being volts times current gives me my power. But we'll talk about that. Nope, it's always going to be no polarities on the actual values of our. It's just a matter of how we put them into the calculators when we need these. All right. So now we have everything all completed. We know that this angle here is going to be at 53.13 degrees negative. So that's going to be my angle from 0 going down this way. So now let's take a look, and now what we want to do is analyze what's going on with our vectors, and then look and see what's happening with our phases. So the first one we're going to look at, we're always going to start referencing everything off of 0 degrees. So I'm looking at 0 degrees, and we're going to look at just the voltage. So at 0 degrees, the voltage of my resistor is going to be at 0 degrees. So I'm just going to put in my voltage of my resistor at 0 degrees. I'm not going to be worried about amplitude or anything like that. We're just more worried about what the phase of all these signals are. So this one here is going to be my VR. That's going to be at 0 degrees. Then my next one then is the other one I want to look at is that, again, just from when we did chapter 9, is that my voltage of my capacitor is going to be 90 degrees out of phase with my resistor. So that means that my voltage of my capacitor is going to lag my voltage of my resistor by 90 degrees. So we're going to do the voltage of our capacitor, and that's going to lag by 90 degrees. All right, then our next one then is going to be my voltage source. This is this one right here. This is our resultant. This is where my voltage total is. That's going to be the length of this line here. That's going to give us our amplitude, and it's also going to tell us where it is in relationship between the voltage of R and the voltage of our capacitor. So my voltage of my source is going to be lagging behind the voltage of my resistor by 53.13 degrees. So slightly more than 45 degrees. So if I know that this is 0 to 90, I know that 53 degrees is going to be somewhere right approximately about there. Just a little bit more over towards my voltage of my capacitor. And that's going to be where my voltage source is going to be at. So if I were to hook up an oscilloscope, and I put on channel 1 on VR, and I put channel 1 on VR, and I put my probe on VS, I would see two of these phase, and I could see that phase shift coming out of there. I would be able to see these two different voltages happening at different times going through my circuit. And then if I did the mass function from VR, if I took my voltage source and a minus VR, then I could get my third waveform, which would be my mass function, and on my oscilloscope I could see all three of those waveforms happening at different times. And so that's exactly what I would see on my oscilloscope. I would see three different waveforms. So even though my voltage source is going up and down, my voltages across my resistor and my voltage going across my capacitors are happening at different times than when it's happening with my voltage source. And if we kind of take a look at it, we kind of look at why that's happening, is because we said that the minute I first apply power to a capacitor, it acts like a what?
Short.
It acts like a short. So the minute I start applying I'm going to draw this a little bit. So here's my voltage of my capacitor. Let's see here. That would be a good. I don't know, that's not a good analogy. But what happens is that when I first apply my voltage of to my capacitor, let's see here, let me put this here. Trying to think of how to explain why that is, but as I because of our current here. Let me let's go one more step here. Before we talk about that, I'm gonna let's do it this way here. If so here's my three waveforms. We got our voltage of our resistor, our voltage of our source, and then our voltage of our capacitor. And then where is my current going to be then? So looking on my vector, where's my current? What's my current going to follow?
BC.
So where's my total current? Where's my total current at? Where do I see it on any one of these? Here's my IT, right? Here's my total current. So my total current is at 0 degrees, right? That's my current is always going to follow voltage of my resistor. So at 0 degrees, I got my IT, IR, since everything remains constant, and then IC. So if we're looking at my current, if I don't have, so my current in my circuit, so when my current starts to, when I start putting in a signal on here, let's see, I'm trying to, I think I'll explain that. So my first applied power to my source.
Well, we know that current leads voltage, so by 90 degrees later, the VC will start to flow.
Right, so, but let's see, so, I'm drawing a blank here. So my voltage source started increasing my voltage. Let me draw. That was going to be behind. I got to draw that way as much here.
I think it was
Because my voltage of my capacitor, so my voltage of my capacitor is at 0 there. Yeah, no current. I'm going to skip that. I know what, I'm trying to make it how to make it simpler. I was trying to use it as the analogy with capacitor acting like a short. I'm bringing it from chapter 9, but I don't know if I like that idea so much. All right, I'll think about it a better way of doing it. But anyways, because I want to kind of explain how we end up with this phase shift. But anyways, so what happens is when I first apply when I first apply my power to the thing, I have a capacitor reacting, so my voltage of my capacitor is either going to be taking in so when my voltage starts to go up, my capacitor is going to start to charge up at the same time there. My capacitor is going to start to charge. It's going to start absorbing some of that energy. Then when my voltage source starts to decrease, then my voltage of my capacitor starts to put back into the circuit. Okay? So when the voltage source goes up, it's going to start taking in, storing some of that energy. And then when my voltage source starts to decrease, then the capacitor is going to put back that energy back into put the energy back into the circuit again. And so it gives us our little phase shift there, because It doesn't happen at the same time. It's going to happen at a later date. And it's kind of based off of, when I first apply power to it, it acts like a short. Then if I keep the power on it for a certain amount of time, then the voltage across the capacitor is going to be at its maximum. When the capacitor is acting like a short, my voltage across my resistor is going to be at its maximum. So for example, when my voltage of my capacitor is at 0, when it first starts to charge up, the voltage of my resistor is going to be at its maximum voltage. When my capacitor is at its largest, and it's taking all the energy and ready to put the energy back into the circuit, my voltage across my resistor is going to be at its minimum. And that kind of gets to be a hard concept to understand, but the theory of it is just that the capacitor is going to be storing energy and then putting it back into the circuit. And then that gives us our 3 different waveforms going into our circuit there. And it's based off of that capacitor either acting like a short or as an open. It's either going to take all the energy or it's going to be putting energy back into the circuit again. Alright, so when I have that going on then, so I'm going to make sure I don't forget about talking about our power. Now when we're calculating our power is always based on the RMS value. That's a heating effect of our resistor. So even if I have my voltage total as if I have my units as peak-to-peak voltage, everything else gets to be calculated as peak-to-peak voltage except for my power. My power always has to be converted into an RMS value and then calculated out. Now when I run this circuit, the only one that's actually going to be putting out true power is going to be my resistor. That power of that resistor is going to be 27 milliwatts. That resistor will actually heat up and produce 27 milliwatts of power. Whether it's a light bulb or just a resistor or a heater or some type that's going to produce 27 milliwatts of power. The capacitor, on the other hand, though, is only going to be storing energy and then putting the energy back into the circuit. It never dissipates any energy. It doesn't give us any light, doesn't give us any heat. And this is what we call our reactive power. It's a reactive power. We're using it for storing energy. And so that's why we just call it, we only give it as 36 milliVAs, volts amp reactive. It's just our volts amps. It's just because there's no true power. Watts is true power, volts amps is just our power. Just kind of like it's a reactive power. We're not getting anything out of it. So when we're combining true power with our reactive power, we get what is called our volts amps reactance. This is our apparent power. This is, then we have so our apparent power is about 45 millibars. Our volts amps reactance. Only a portion of that 45 millibars is actually giving us any true power, and that's coming off the resistor. The remainder of it is all the reactive power. So the power company is going to charge us for 45 millibars, where in turn, though, we're only really actually getting 27 milliwatts out of our circuit. But we get charged for the 45. And those are volts amps reactance. And always calculated out using the RMS value. Pretty straightforward. That's as easy as it can be, right? But if I were to hook that up to an oscilloscope, though, I would actually literally see all 3 of those waveforms going on all at one time. I'm going to think about my... Yeah, so I'm trying to think of how I'm trying to think on how I normally explain that capacitor thing. But anyways, that capacitor is just storing and putting energy back into the circuit, and the resistor is actually giving us our true power. All right, let's take a look at one more here. Like I said, we got we'll practice this until it'll all make sense here. But make sure you read your chapter. I mean, you can just see the complexity of this. All right. So what's my first step? To solving for all our fill in the blanks there. What's my first step?
Graph the points, I guess.
What's that?
Graph the points.
Yeah, the first thing I would always do is I would kind of graph those points, put those on my vector to find out where we're at. So R is going to be right here. So here's R. So we're at 6 kilo ohms. So I'm just going to go 1, 2, 3, 4, 5, 6. Put a dot there. X is going to be where?
Negative.
Negative. And that's going to be our -8. So it's going to be 1, 2, 3, 4, 5, 6, 7, 8. So then I know that I'm going to get an angle somewhere about here. So from the center here, drop. And that's going to be, the length of that line is going to be my voltage total, my impedance total, and my power total. All right, then what's my next step?
Find DT.
Yeah, find the ZT. If we know two things, we can always find the third. Just the same thing when we're doing trig. Once we know two, we can find the third. So what do I get for ZT then? And make sure that you put in make sure you remember that this is plus X and this is negative Y. So when we're entering in the calculator, we have to make sure we put in our polarities.
I think it's 10K.
All right, what do I get for ZT? What'd you get?
10K?
10K ohms?
Mm-hmm.
Everyone agree with that? All right, they get 10K ohms. Okay, so that was our step one there. Okay, then what would be my next step?
Getting the angle?
Yeah, figure out your angle at the same time. Since we already have those numbers in there, figure out what our angle is. So what's our angle going to be?
53.13.
Negative
Negative.
53.13 degrees. Same as the last one? Yep, there it is. It's just the values have just doubled, haven't they?
Yep.
How come if I put in Y as a positive, I get 10 kilo ohms? If I put in Y as a negative, I get 6 kilo ohms.
The degrees of change.
Let's see. Say that one more time.
When I'm figuring out the ZT, if I put in Y as a positive, I get 10 kilo ohms. But if I put in Y as a negative, I get 6 kilo ohms for ZT.
No, you shouldn't.
Then I like 5 times.
Yeah. Just take a quick look. Just show me when you get. Show me your wrong way that you're doing. Show me how you're doing it wrong. Then when you put in 8K for positive, you're saying? No, but if you put it in as a negative, you get. Oh, you probably put it in, maybe you know, it was on the exponent, was it? Yeah. Make sure you put your negative in before you hit your exponent key. Yeah. Yep, so you should get 10K and then you should get your 53.133s again. Alright, then what's our next step?
Solving current.
Yeah, figure out your current. Get that current taken care of. So what do I get for current on this one?
1 milliamp AC.
Yep, 1 milliamps AC. Good. Okay. Then what's my next step?
Fill in the blanks.
Fill in the blanks. Fill in the last one. Fill in my power. And I can just use Ohm's law for it on this one. So what do I get for power? 10 millibars. Volts, amps, reactants. When you're putting in bars, I'm trying to say that out so you know it, so you remember what that unit is. So 10 millibars or 10 volts, amps, reactants. Combination of my true power and my reactive power. All right, then what's that? Oh yeah, don't forget to fill in the rest of our currents. No, we should have done that on that first
That's
step.
what I meant by blank.
And now we can figure out our voltage. We can just go ahead and pretty much we can do everything with Ohm's law now. Once we got that angle, and we got our impedance total, everything else, and we got everything else, we can just go ahead and do Ohm's law and everything else we want to. Or we can go ahead and do our polar to rectangular function, whichever we want to do. If you do your polar to rectangular functions, all you have to do is put in your voltage once and your angle once, and then you can calculate out both your voltages across your resistor and your capacitor all at the same time. If you put in your voltage and your angle, then the first time you hit your rectangular or your polar to rectangular function, they'll give you a VR, and then you hit it again, and it's going to automatically give you your voltage and capacitor. Otherwise, you have to calculate it out twice. But what's voltage across VR? Six millivolts? Should get 6 volts. Yeah. Sorry, 6 volts, yep. And then the voltage across my capacitor should be straightforward. 8 volts. So you need a calculator for those. Okay? And then my power. So 8 volts times 8 milliVAs. And then my power across my resistor, 6 milliwatts. Good. Our true power and our reactive power. And all those numbers are all, whether it's power or anything, I can use those as my vectors. My power, I can use as a vector. That's going to be in the same length, same XY locations. My voltage, the only thing is my current. My current is always going to be, all three of my currents are going to be right here. My IT, IC, and IR. Those are all going to stay right at 0 degrees. All right, so what goes at, so if I do my phases then, what starts out at 0 degrees?
VR.
My VR. So my VR is going to be here. Then where's my voltage up my capacitor going to be?
90 degrees from that.
90 degrees behind it, lagging it. Make sure you use the word lagging. So that's going to be my BC, VR, and where's my BS?
52.8, 53.3, or 93.3.
Okay.
90 degrees.
And that's going to in relationship to what? Which one? And this is the VR. So it's going to be lagging. So my BS is going to be lagging my resistor by 53.13 degrees. That's going to be where my BS is at. And then where's my current? Where does my current start? At what angle?
With VR.
With VR. My current is always going to follow VR. IT, IC, and IR. They're all going to be right at 0 degrees. Okay? And then from here to here, my BS is going to be lagging VR by 53.13 degrees. Okay? So then another thing that to look at real quick is that what is, we've done about 2 minutes here. So now when we're looking at this circuit then, the other thing that we're looking at is, when I consider this thing purely capacitive, or when I consider it more capacitive or more resistive on this circuit. So what I'm saying by that is that here's my BS, okay? If BS is always following VR at 0 degrees, that means I would have no capacitive reactance in there. The resistance of DC would, or my capacitive reactance of my capacitor would be at 0. If I was purely capacitive, then that means I wouldn't have any resistance, and I'd be purely capacitive. So when we're looking at this, am I more capacitive or more resistive?
Capacitive?
More capacitive. Okay? And it holds true because my capacitive reactance is at 8 kiloohms and my resistor is at 6 kiloohms. So I'm more capacitive at that time. And when it's more capacitive, that means that my voltage source is going to be following DC more. If I were to drop this resistor out and short this out, VS would follow DC. If I drop my capacitor out and short that out, then my VS would follow VR. And so this voltage source we're going to see tomorrow, we're going to see that that's going to be kind of shifting in between VR and DC, and we'll take a look at that tomorrow. All right, that's a wrap for today.